So after all the preparation of the last lectures, we are ready now to enter the core of the theory, and so this famous theorem of the cone by Shigefumi Mori. Before this, let me state another result that I don't think I have time to prove, which is the so-called boundedness of denominators. So take H, X, projective surface, okay, H, ample divisor, and take Kx not an F. Then writing Th, the net threshold, as A over B. Recall that this, by the rationality lemma, this is a rational number with ZCD of AB equal 1. Then the denominator is at most 3. OK? So if you prefer. OK. So the proof of this is similar, follows from the base point free lemma, from the rationality lemma. I don't think I have time to do this. If there is time at the end, maybe I can sketch it. Otherwise, you can find it in the references I gave, for instance, in Ciliberto's notes or in Miles' Reed book. OK, now let me state the famous cone theorem. I will explain to you why this is necessary, it's important. Theorem of the cone. In the 80s. So let me state it in generality. Let X, generality in the smooth case, be a non-singular projective variety over C. Everything is complex, so one. There are at most countably rational curves Ci such that in X, such that they are Kx negative, and the self-intersection actually is bounded. With the intersection with the canonical is bounded. And the Mori cone is given by, expanded by the Kx non-negative part and by the ray spanned by these curves. Sigma. OK, actually this spans some extremal rays. I will write a remark later. And 2, so this is 2. OK, for any epsilon greater than 0 and any ample class, there are only finitely many of these curves such was class lie in the region kx plus at epsilon h negative, and we have again the Mori cone is spanned by the positive part with respect to this hyperplane and this finitely many now rays. I wrote here G1 Ck, so T from 1 to K, R. Okay. Remark, the rational curves Ci spans generate distinct extremal rays contained in the half space this one, Kx negative. Okay, and notice that this condition 2 means that whenever I take an hyperplane, which is not Kx, a little bit before Kx, then there are at most finitely many of these extremal rays. So the extremal rays, these extremal rays can accumulate. There are examples, and I will show you one famous due to Nagata. But when these extremal rays accumulate, the only possibility is that they accumulate over the hyperplane Kx orthogonal. The only possibility is that they can accumulate on Kx orthogonal, not over another hyperplane. I will show you a picture. Okay. Note that condition 2 tells us that the extremal rays R spanned by Ci can accumulate on the hyperplane Kx orthogonal, but not in a hyperplane of the form Kx plus epsilon h orthogonal, since in the half space here the cone is polyhedral. Since there are finitely many of these extremal rays. So the picture, if you want, is this one.
Is projective variety or projective surface?
No, this is variety. This is in general. But for surfaces, these are also smooth. So you can say much more. I mean, no, this is for projective variety. There are, of course, there are also versions for singular varieties. But yeah, in Collar-Mori you can find some version for singular varieties. But this is for this is the general statement for smooth projective complex varieties, and for surfaces we can say more. I will. For surfaces, these curves can be taken smooth, and they are very particular curves. Okay, the picture is the following. You have this Kx orthogonal hyperplane. Okay, so as usual, I will draw the cone by a section. So this is 0. Okay, this is a Kx negative part. This is the Kx positive part. Regarding the Kx positive part, the cone tells us nothing. We don't know. Let me draw something like this. Regarding the Kx negative part, we know a lot of things. There are some extremal rays here. These rays can accumulate here. Might. So it can happen. It can happen. It's not necessary, but it can happen. These are extremal rays. Very good. Here, maybe there is this hyperplane H. Recall that as I said yesterday, by Kleiman criterion, this does not intersect the cone. And then there is this other hyperplane, which I obtained by just slightly modifying this one by adding some small multiple of H. And this is. And here, we have just finitely many extremal rays. They cannot accumulate on the green hyperplane because of this condition. Because of this condition. OK? So here, and in this region here, just finitely many rays here. In this region, I mean. OK, so there is a Kx positive part we don't know nothing about. There is a Kx negative part. In the Kx negative part, the cone is spanned by this countable family of extremal rays generated by rational curves. These rays can be infinite in number, and they can, it's not necessary, of course, but they can accumulate on this hyperplane. But if I take an hyperplane on the form Kx plus epsilon h orthogonal, where epsilon is greater than 0, then in this region there are just finitely many extremal rays. The cone is polyhedral here, so there is no accumulation on this green hyperplane. This is not possible. The only possible accumulation is on the red hyperplane. OK? This is the Mori cone. This is the theorem of Mori. And this was a big surprise in the 80s because, OK, for surface, this is for surface curves and divisor are the same thing. But for higher dimensional varieties, this is not true anymore. And Mori actually said, OK, the right thing to look at is not the cone of divisor. I mean, it is an interesting object. But we can say a lot more about the cone of curves. The cone of curves really governs the geometry, at least in the Kx negative part. And this was the big revolution by Mori, in fact. Using these results, he was able to give the classification of contractional threefolds. And this was a shift of paradigm in birational geometry in the 80s, looking at the cone of curves instead of the divisor as before. OK. This is the Okay. This, let me say something. This one. No, of course not. This one. Okay, the logical order of the treatment is the following. I have no time to prove anything, but the logical order, logical, I mean, the one you find in the books of the treatment, is the following. We have rationality lemma. This in base point free lemma. And this implies the boundedness of denominators. And all of this imply Kohn theorem. We must say that in the smooth case, it's also possible to first prove the Kohn theorem in Mori book. This is problem first in the smooth case, and then you can prove these results. But in the singular case, the Kohn theorem is much more difficult. So a direct proof is more complicated. So usually the treatment, in the general case, the treatment is this one. The Kohn theorem is obtained as corollary of all these results. Anyway, I will not prove the Kohn theorem. I want to give some interesting examples and apply it to the classification of surfaces. However, let me say that, for instance, what are the boundaries of denominators you said when you prove that there are finitely many extremal rays in any hyperplane of the form kx plus epsilon h orthogonal. When you do the computation there, you see that boundaries of denominator enters the game. Because, I mean, you can find it, for instance, in Chiliberto lecture knows this. Anyway, let me give some examples. Example 1, Fano varieties. So, definition, X smooth projective, X is called Fano, if kx minus kx is ample. So if minus kx is ample, by Kleiman criterion, this means that the whole cone, apart from the 0, is contained in the half space What does it mean? It means that then there is no accumulation, because the whole cone is strictly contained in the half space kx negative. So this means that there are finitely many extremal rays that spans the cone, and there is no kx positive parts. So, in particular, by the Kohn theorem, there is only a finite number of extremal rays C1, Ct, spanned by rational curves and such that minus kx times ci is at most dim x plus 1. So, in this case, the cone is polyhedral. Is closed at the polyhedron. Polyhedral. Well, it is closed because it's generated by a finite number of extremal rays. And in fact, we have how many Ct okay. So the situation is I have this Kx orthogonal. There is nothing here by Kleiman criterion, and everything is here. This is 0. I'm drawing the section as usual. This is a section of the cone. Finite number of extremal rays here. Okay. So there is nothing here. Everything is here. Everything is polyhedral because there are just finitely many extremal rays. Particular case, Fano surfaces, the so-called Del Pezzo surfaces. The classical denomination is Del Pezzo surfaces because of Del Pezzo, who studied them in the classical period. So in this case, the extremal rays satisfy, well, minus kx ci is at most dim x plus 1, and this is 3. And so, by adjunction formula, ci is, okay, let me say that ci squared is between minus 1 and 1. There are 3 cases. If ci squared equal 1 for some I, okay, we have an extremal ray spanned by a curve with positive intersection. And by a result, I said 2 days ago, I think 2 lectures ago, or something like that, In this case, the Picard number is 1, and actually, we can prove that the variety is isomorphic to P2. Okay, since in this case, rho of x is 1, we know that rho of x equal 1, and since minus kx is ample, we can prove, and this is not completely immediate, we must work a little bit, that x is isomorphic to P2. Okay.
So for the adjunction formula, somehow you need to know that the arithmetic genus of the curve.
Yeah, you must know that arithmetic genus of the curve is positive. It's not negative, right? We have PA of CI is this is irreducible. This is irreducible, so this is non-negative, and this is, I think. So if this is minus 3, so this means that this can be minus 1, minus 2, and minus 3. And you obtain that this must be between minus 1 and 1, right? Because you have that, okay.
Well, the curve is rational, but it might be a singular rational.
Yeah, actually, for the case of curves, for the case of surface, you can prove that they are smooth. There is no way to, yeah. I have no time to explain everything, but in the case of surfaces, you can prove that in this case, let me make a remark. I mean, the logical way to do things is that one can first prove the Mori theorem in the case of surface. When you go and prove the extremal contraction theorem, then you see that all the curves in this extremal rays in the case of surface are smooth. And so when you make examples, you are OK. But I want to give example before. So let me say that in the case of surfaces, I don't want to do all the results before and then the examples. So I want to give these examples now, and then let me say that in the case of surfaces, one can prove that all extremal rays in the Kohn theorem are not only rational, but actually smooth. I think this is false in higher dimensions, right?
I don't have an example.
Yeah, I don't have an example on the top of my head. Anyway, not only rational, but actually smooth. OK, thank you for the remark. So in this case, plus smoothness of the CI. We have this, OK. Another case is the case where if CI square is 0 for some I. So in this case, we know that rho of x is 2. This is one theorem I said I stated some lectures ago, and x is roulette over a smooth curve. Very good. On the other hand, we have that the irregularity, which is h1 of x, kx, this is h1 of x minus kx. Recall that this is also h0 of x omega. Yes. 1, 0, 0, 1. OK. And this is ample. So this is minus something ample, and h1 is 0. So this surface has vanishing irregularity, and so it's ruled so over P1. And so because this is a standard argument, if I have some non-zero 1 form here, I can pull back here it over x. So I will find something here, but something non-trivial here. But there are no global 1 form on x. And so this must be P1. I have no global 1 form here, and so this must be P1.
This can be any of the ruled surface.
Eh?
Any of the ruled surface or P1 can be.
No. This is Fano. So, I mean, in this case, either is P1 cross P1 or is Erzebruch surface, yes. F1. OK, so in this case, no global 1 forms. OK, and the possibilities here are x, this is P1 cross P1, the quadric, or x F1, which is the blow-up at the point of P2. And these are both Del Pezzo surfaces, and they are the only one which are fibred. Finally, the case in which all these curves have negative self-intersection. So, OK. I mean, the anticanonical ample is very restrictive. So, OK, let me leave here and just finish this before. OK, finally, if case 3, if secant I squared equal -1 for all I, then all the secant I are -1 curves, smooth rational curves with self-intersection -1. In this case, it is known that x is the blow-up of, OK, P2 at 9 minus m general points with m between 1 and 8, and the Picard number is 1 plus m, and the anticanonical system is given by the cubic passing through these points. Because you said the case. Yeah, that case belongs to. In some sense, F1 is, you can see it as del pezzo as a Mori fiber space is also in this case. I mean, it's such in the intersection of the.
Changing basis, you mean?
No, I mean that you can see it as a blow up of P2, but also as a ruled surface. So it's the only case in which you can do this. The other blow up, yeah.
There is one cover.
Yeah, of course. And yeah, I understand what you say. I said a little bit sloppy. You see, for all I, yeah, how to say this? For some E, yes, okay. P1 cross P1. Okay, let me say in this case. Because that case, yes. I don't want to start. Because in the case of F1, we have, in the case of F1, the Mori cone is like this. You have the fiber here, and here this is the -1 curve. So in this case, okay, yeah, maybe. Let's say, as you say it. So no, 2. Okay? Okay, 2 point. N minus, okay. N minus. So 1, 7, okay. The case, the blow up at one point is covered by the previous case. Okay. Okay, and we know that in this case, the integer minus m is called the degree of the del pezzo. Okay, and this is known that minus kx is very ample as soon as the degree, let me call d is at least 3. The number of points is at most 6. Otherwise, it's clear it cannot be very ample because, for instance, if you blow up 7 points, you have a linear system of degree 2. So it is a double cover of P2, the map associated to minus k, branched over a quartic, I think. Okay. A particularly interesting case and classical case, M equals 6, D equals 3. So the blow up of P2 are 6 general points. These are general. Okay, general. So in this case, the linear system, the very ample linear system minus kx defines an embedding of x in P3 as a surface or degree 3, as a cubic, smooth cubic. Okay. Very good. Okay. The Mori theorem yields that you have the Mori cone is closed, and it is given by, okay, let me recall that this is very classical. Every such a surface contains 27 lines. And all of them are -1 curve, are exceptional curve of the first kind. So it contains 27 lines. This is, I think, due to Salmon, anyway, it's English or Irish result. This is not Italian. Right? No, no, no. The 27 lines is not an Italian result. It's an English result, I think, or Irish. I think it's Salmon. We can check. Okay, anyway. I don't think so, Castelnuovo, this. So, in this case, this is generated or Sylvester Cayley, maybe Sylvester Cayley. By these 27 lines, which are the only -1 curves inside the surface, and this is contained in the Picard number is 7 because I'm blowing up P2 in 6 points. Okay, and this is N1 of X. So the cone of the Del Pezzo surface of degree 3, which is a smooth cubic in P3, it is closed. It is generated by 27 extremal rays. All of them correspond to -1 curves, and it lives in R7. Okay, and the class of the 77 lines, the class of the 27 lines are the class of the exceptional divisors, we have a blow up in 6 points, so this is the exceptional divisors. Then we have the lines through 2 of these points, all the possible lines. So we have lines minus AI minus AJ. Classes of lines through P, E, P, J, and then the class of conics through 5 of these points. So 2H conics minus, let me write in this way, A1 minus A6 plus EI, where E is between 1 and 6. You are blowing up 6 points. If you take a line through 2 of these points, the blow up is a -1 curve because the self-intersection drops by 2. 1 minus 2 is -1. Again, a conic, a self-intersection 4. If you take a conic through 5 of these points, you are getting the self-intersection dropping by 5. 4 minus 5 is -1 again. And so Here you have 6. Here you have 6 over, yes, 6 over 2. That I think is 15. And here you have 6 again, because, and the total is 27. This is very, very, very classical. OK. And now, some more pathological examples. Nagata's example of a cone of curves which is not finitely generated. OK, I will not prove everything, but I will say something. OK, so I deleted the statement, but I said that in the cone theorem it's really possible that there are infinitely many extremal rays, and that these extremal rays can accumulate on the hyperplane Kx orthogonal. And this is one example of this kind for surfaces. So in some sense, it's the step after Del Pezzo. I mean, because in the Del Pezzo case, we are just blowing up at most 8 points, OK? And what happens if we blow up 9 points? When, if we blow up 9 points, something wild happens. Because the surface change is not Del Pezzo anymore, the anticanonical is not ample anymore, and really something strange can happen. Let's see. Let pi from x to p2 be the blow up at the 9 base points of a general pencil of cubics. General, for instance, it suffices that all curves are irreducible. It is well known. I think if you take a general pencil of cubics, then the most general one contains 12 nodal fibers. But there are other situations in which there are cuspidal fibers and so on. They are good as well, as soon as all curves are irreducible, nodal or cuspidal. Anyway, you can think about a very general pencil with 12 nodal cubics. OK, and let. So what happens now? You have these cubics here. One, two, three, four, five, 6, 7, 8, 9. And maybe some of them will be nodal. Maybe, surely. OK. Since the cubics intersect at 9 points, and we are blowing up the base locus here, what happens is that we obtain a vibration without base points. So the up over P2, let phi from x to P1, the elliptic vibration given by the strict transform of this pencil. So we are in this situation. This is P1, a pencil of cubic. I have here some smooth elliptic curve. Then I have some nodal one, not important, a finite number of nodal ones. And then I have 9 sections corresponding to the exceptional divisors. So let me maybe, this is, this one, corresponding to a fiber here. And the nodal one corresponds to the nodal fiber here. And the points that I'm going to blow up corresponds to sections. One, two, three, four, five, six, seven. One more. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, it's okay. It's okay. 9 sections. They cannot pass through the node because the intersection must be 1. So they are outside the nodes. 1, 2, 3, 4, 5, 6, 7, 8, and 9. OK, 9 sections. Let me call them echo 9. OK. The exceptional divisor E1, E0, E8, let me call it this way, are sections of phi. We choose A0 as a 0 section. So we can get a group of automorphisms. There is something that must be done, but let me write in this way. Of X via translations using the group law of the fiber by the remaining 8 sections. So these are elliptic curves. I'd say that this is 0. So there is a 0 everywhere. And I use the other section in order to translate. And this can be globalized. This can be globalized because, one must work a little bit because this don't pass to the node. So the group law can be extended here. And you see that you can globalize this translation from one fiber to all the surface. And moreover, one also show that since the fibers are not reducible, then this group of automorphisms that we obtain is not finite, is infinite. And in fact, is isomorphic to z to the 8. One can show that the group, the subgroup of out X constructed in this way anyway, let me say that some details are needed. But essentially, this is what happens. OK, one can show that the subgroup of out X constructed in this way is isomorphic to z to the 8. In particular, is infinite. And here, we must use the fact that the pencil is general. I think. Anyway. OK. So what happens? What happens that we translate with an infinite group of translations. And so what happens is that we obtain infinitely many -1 curves. So X contains infinitely many -1 curves. Okay. And the fact is that the degree of this is not, the kx degree of this is not bounded. We can see this. Okay, so we have a case of a surface with infinitely many curves of the accessoral curves of the first kind. So this means that kx a sigma is -1. This is equal to E sigma square. And so E sigma is isomorphic to P1. For a result we saw before, every curve of this type must span an extremal ray of the Mori cone. So our Mori cone has infinitely many extremal rays in this case. No. Okay. So the class of the E sigma are all spanning extremal rays of in of x. And we know by the Kohn theorem that these extremal rays, the only possibility, they are kx negative extremal rays. Yes, is there? Kx E sigma is -1, so they are kx negative extremal rays that are all kx negative. By the Mori cone, the only possibility is that such rays accumulate on the hyperplane kx orthogonal. So, in this case, the cone is not finitely generated. If you have infinitely many extremal rays, it cannot be finitely generated. It's not the convex hull of a finite number of extremal rays. So, in this case, an E of x is not finitely generated. And the picture is the usual. And here we don't know very much what happens. This is the kx negative part, and this is the kx positive. note that in this case, remark 1, in this case, kx is an f, but not ample. In fact, minus kf. In fact, minus kx is just the elliptic vibration. So note the difference between the ample case, minus kx ample, and the case where minus kx is an f but not ample. Just blowing up a point, we obtain this mess. So the Mori cone is a very subtle invariant. It's a very subtle invariant, because in this case, the difference between the two surfaces seems something, just blowing up a point. But when you blow up a point, you transform a perfectly good cone, a polyhedral cone like this, in something like this. Remark 2, we don't know very much about this part. It is conjectured that it is circular. That it is spanned by class of non-negative intersection. But this is related to some important conjecture in birational geometry, for instance, Hirschowitz conjecture. Yeah?
I have a remark about this. So there's a paper by Prendergast-Smith proves that if you blow up P2 and 9 very general points, so not even base points, then actually the intersection of the Mori cone with Kx or orthogonal is spanned by minus Kx. But this is really, one very special case where someone figured out how to do it.
Thank you.
Nice.
Thank you. Okay, let me say it in this way. It is conjecture. It is circular. By the way, about this, one can think the following thing. Okay, but you have this particular example because you built this surface with a huge group of automorphisms. And so you have this huge group of automorphisms given by translation by these sections. And so you take -1 curves, move this -1 curve, you obtain such a mess of -1 curves. But actually, there is a fact quite surprising, and is that -1 curves are stable by small deformation. So if you make a small deformation of the surface, they do not disappear. So you can take these points here, just move a little bit. They are not the base of a pencil of curves anymore, but the -1 curves are still there. In this case, the surface will have no automorphism at all. But still, the Mori cone is not finitely generated. This is for me, this is quite surprising, because this shows that this feature of having not finitely generated Mori cone is not strictly related to this infinite automorphism group. It's something subtler. The point is that -1 curves are stable by small deformation. So if you build an example in which there are infinitely many of them, if you make a small deformation, they are still there. Even if the automorphism group is killed. Okay. Now, there are other things that we can say, but the time is short, so let me talk about the end of the classification. In order to classify surface, we need to arrive at some minimal model, In order to arrive to some minimal model, which means essentially that they are fibered with fiber P1 or with Kx ample, Kx and F or P2, we will see, we need some tool that allow us to contract extremal rays. This is so-called theorem of extremal contraction, which also, for instance, in the Conlar-Mori book, you can find it stated for trefolds, and the local nature of contraction for trefolds is more complicated. Let me state it for surfaces. Before all this, we need some preparation. Okay. Theorem of extremal contraction. Okay. Let me start with a lemma of the supporting hyperplane. Okay, let R x projective surface take R be an extremal ray, be a Kx negative. Extremal ray okay, then there exists a Nef but not ample divisor dr such that we have dr times z is 0 if only if z is in R. Equivalently, this means that if I take the Mori cone, I take the intersection with dr orthogonal, what I obtain is R. So you can always find an hyperplane supporting R, exactly R. Oh, the idea of the proof this follows from cone theorem plus rationality theorem. Okay, take okay, and E of x is locally polyhedral in N E of Kx negative. Oh, okay, away from Kx orthogonal. Well, and so we can find an F R divisor M such that M orthogonal intersection NA of X is R. This is just convex geometry. But I want a rational divisor. In order to take a natural divisor, I can do the following. To have a rational divisor, I can do the following thing. I know that since, and this is an F, an F, okay. Since amp of X is the interior of an F, I can find an ample Q divisor H very close to M. Of course, everything must be justified, and in order to make this legitimate, we need some calculation, but we can do it. Okay, then the divisor, the R, which is H plus TH KX, is an F, but not ample, Q divisor. And this is Q divisor by rationality lemma. This is Q divisor that satisfies the requirement. More or less, the proof is in this way. So the idea is very simple. I mean, you have this equation here. You have your cone. Assume that this is R. So by convex geometry, you can find a hyperplane supporting it, because here is polyhedral, away from Kx, orthogonal. This is M. This is an R divisor. It's just an R divisor. But now, you can move it a little bit by density of amp. We can find an ample divisor very, very close to this. Okay. And now, just to take the net threshold here, this means that I move here and I make it touching the boundary again, but in this case, as a Q divisor. And of course, the support, this new divisor, this Q divisor, will, by continuity, will support again just R. Let's say this way. This is the R. So take a real support divisor of the extremal ray, move it a little bit to an ample divisor, take the net threshold of this ample divisor, and then H plus THKX is a Q divisor, satisfying the requirement. And you see, as in this case, the rationality lemma is absolutely essential because. Okay, so theorem. Contraction of Kx extremal rays in dimension 2. Kx negative Okay. Let X be a smooth projective surface for each extremal ray R contained in the half space Kx negative, there exists a morphism phi R from X to Y called the contraction of R such that 1 phi R as connected fibers and Y is smooth and projective and 2 okay, given a curve C in X, we have the R of C equal point if only if C in R. Okay, time is short, unfortunately. How much time I have? 10 minutes. 10 minutes, so I have to just give an outline, very short. But so this theorem says that, okay, if you have a Kx negative extremal ray, then you can contract it in the projective category. And in fact, what you obtain is that you go to a smooth variety. And part 2 says that if there is a curve which is contracted by this morphism, then all this morphism contracts precisely all the curves which are numerically equivalent to it. So there is a contraction, which is contraction of extremal ray of the cone, means that you are constructing a numerical class of curves. And there are 3. I have no time, unfortunately, to say everything in detail, but just you can find the proof in the references. Just and the proof uses this support hyperplane here. Idea. Okay, the idea is take the R such that NE of X intersection dr orthogonal is R. MdR is base point free for M very big. This is a base point free theorem. Okay, then, and sufficiently divisible. Then, phi R will be just the map associated to this base point free linear system. Okay. Actually, there are 3 cases. And so there is this corollary. Contraction theorem. dimension 2. Allora, same assumptions as before. Okay. Then the contraction phi r from x to y of the kx negative extremal ray is one of the following. One, y is a smooth surface phi r is the contraction of a -1 curve okay, to a smooth point, and in this case, R is exactly the extremal ray spanned by this. So we have that kx times E is -1. 2, y is a smooth curve and x is a P1 bundle over y. Okay, in this case, the extremal ray is generated by the numerical class of a fiber. And kxf is -2. And finally, 3, y is a point. In this case, minus kx is ample, and actually we can prove that it's isomorphic to x is isomorphic to P2. In this case, R is given by the extremal ray spanned by a line of P2, L line. And so kxL is -3. So we have the 3 cases of the Kohn theorem. Recall that by the Kohn theorem, minus kx for the generator of the extremal ray is 1, 2, or 3. So minus kx is -1, -2, -3. And we have all 3 possibilities. So summing up, when I have an extremal contraction, in the case of surfaces, we have one of these cases. I'm contracting a -1 curve to a smooth point, or I'm contracting a fibration, so I'm over a curve, so I'm obtaining a P1 bundle, or I am in the P2 case. So the outline at the end of the story, there is a product of this Wilson algorithm that I have a surface, and using 1, 2, and 3 infinitely many times, I can arrive to either a smooth surface with kx nef, or to a smooth curve, or to a point. And these are the these are the product of the minimal model program. So let me just state 1 minute to the final statement of the course, which is MMP in dimension 2. In this case, note that in this case, rho of y is rho of x -1. Okay, so So we can apply 1, 2, 3 repeatedly. In the sense that we have an algorithm producing a so-called minimal model yes, 1 minute, more precisely. Theorem M minimal model program in dimension 2. Okay. X smooth and projective. Surface. Okay. There is a sequence x, x1, x2, finite. Xn, which is y of contractions, such that y falls in one of the following cases. One, ky is an f. 2, y is a P1 bundle over a smooth curve. And 3, y is isomorphic to P2. So this is the so-called outcome of the minimal model program in dimension 2. You take a surface, you apply, if kx is an f, nothing to do. The surface must be investigated in other ways. If kx is not an f, you have a kx negative extremal ray, you can start contracting. So we are in the case 1, 2, or 3. If you are in case 2, you are done. If you are in case 3, you are done, because these are just, structure result. If you are in case 1, you have again, kx is not an f. If ky is an f, you are done. Otherwise, you can proceed. You can go on. At the end of the story, you must terminate your algorithm, because here you terminate, and here, whenever you apply this one, there is the picker number dropping by 1. So you cannot apply this infinitely many times. So at the end of the story, you obtain something which is with ky and f, or something which is a P1 bundle over a smooth curve, or something which is P2. And this is the classification, the minimal model program in dimension 2. Just 10 seconds. Of course, the big idea of Mori was to use this stuff in order to classify trifles, for instance. In the case of trifles, something different happens, because there are the extremal contraction can be classified, but in some case, they introduce singularities. Y is not smooth anymore, but in some cases, when you apply extremal contraction to trifles, there are cases when Y is singular. And so the philosophy of Mori is that you cannot avoid the singularities when you want to study minimal model in dimension at least 3. If you want to study minimal model in dimension at least 3, the correct point of view, at least if you want to follow this strategy, is to allow singularities. They do not appear in dimension 2, because in dimension 2, the minimal model that we obtain is always smooth, is either a smooth surface with canonical f, or a smooth P1 bundle, or P2. When you start applying this stuff in dimension 3 or more, something different happens. Singularities enter into the game, and so one is forced to study these singularities. And for instance, there is the concept of canonical terminal singularities, and so on. But this is a much bigger story, and of course I have no time to talk about it. So I just thank you for the attention, and I will stop here. Thank you very much.